Okay, so far, when it comes to the subjects of finding solutions to nonlinear equations, we have looked at some types of methods which fall under different groups. For example, we looked at the bracketing method last year, and under the bracketing method, we looked at bisection. Then this year, we also looked at another bracketing method, which is the force position method or regular force method, which is a bracketing method. Then there is another type of method which you could use, which is what we used last year, where you make slopes, or what are referred to as open methods, where we had the Newton-Raphson method. We also had the second method, which was what you use there. Okay. Now there is another way in which you can work out these things, find solutions to these equations, nonlinear equations, by doing what is called repetitive substitution. Okay, so you kind of you have some function, then you put something in this particular function. For example, the way we have here. So when you are repeating things over and over, then we say that basically when you're using computers, we say that you're doing an iteration. To iterate is to repeat something over and over until you get the kind of answer which you want. Are we clear?
Yes, sir.
Yes. So in this particular case, you have a certain function, which is this function g, which is a function of x. Okay, yeah, with the function g, which is a function of x. Now, in this function g, which is a function of x, you put in your guess or your starting value of x. Are we clear? In this function g of x, yeah, with the function g of x, you put in a starting value of x. When you put in a starting value of x, it's going to give you another value of x. Okay. Now the whole point here is, as you are doing this process, then you get a value of x, you put it back in, then this function gives you another value of x, you get this value of x, you put it back in this function gives you another value of x. Now as you are doing this, you're doing this repetitive process, which is called an iteration. The point is, hopefully, with this type of function you're using, the value of x you started with is going to give you another value of x, which is eventually going to lead you to a fixed value of x, a value of x which is not going to change. So you're basically going to be approaching a particular value. Are we clear?
Yes, sir.
That's why the name says fixed point. The whole point of doing this repetition is so that you approach a particular fixed value of x. So you start with a certain value of x, then you put it in this particular function, this function g of x. Then this g of x is going to give you a value of x1, is going to give you a value of x. So if you start with, let's say, x equals to 0, when you put x equals to 0 in this function g, it's going to give you x1. Okay, then you get your x1, you put it back in this function g, then it's going to give you x2. That's what we are hoping should happen. Then you get your x2, you put it in this particular function g again, then it should give you x3. Okay, basically that's what's going to happen. Then you get your x3, you put it back in this function g, then it should give you x5. Then you get your x5, you put it in this particular function g, they should give you x6. Then you get your x6, you put it in this function, you insert it in this function g, should give you x7, like that. Now two things can happen. Either as you are doing this, getting the value of x, you put it in this particular function, you can start approaching a certain value. When you start approaching a certain value, then we say that the function is converging, the iteration is converging. This whole process which you are doing, this repetitive process which you are doing, is leading you towards a certain fixed value of x. So that's what we say That's when we say that there's convergence which is happening. Okay. The other thing which can happen is you could have made a bad choice of what function of x you're supposed to use. Because you have to come up with this function. We give you some equation, a nonlinear equation. Out of this nonlinear equation, we give you a nonlinear equation of x. Okay? We give you a nonlinear equation of x. Then out of this equation of x, you form a function of x. You create a function of x. As you create this function of x, this particular function which you would have created, sometimes you could have you come up with a function which doesn't work so well, such that when you put in your x1 here, you put in your x0, you get your x1, but your x1 starts moving away from anything, from your whatever you started with. Then you get your x2, you put it back in here, then you get your x3, then your x3 is further away, it's not going towards anything. As you keep on doing this, you realize that after a certain amount of time, your function is not, your values of x are not approaching any fixed value of x, any fixed point. So in such a case, we say that your function is diverging. Okay? So as you can see, basically with what we have been doing, with bracketing method, for force position, with bisection, and all these other things, with computers, when it comes to this business which you're in with computational physics and everything, you have to repeat things over and over and over. Okay, and this process of repeating things, this is basically what is called an iteration. And these iterations, this thing of doing iterations can be used to find, as we have seen before, roots of equations. We have used bisection, where we repeated things. We did Newton-Raphson method, where we repeated things. We did a second method. We also did the same thing, and we also did the force position method. But you can use iterations also for other things. For example, for finding solutions to systems of linear equations. Last year, when we did the systems of linear equations, we used Gauss elimination with pivoting. We also used LU decomposition, but we could also do the same stuff by simply doing iterations. You could also use the same iterations to find solutions to systems of nonlinear equations, as we are going to see in this course. The other thing you could use iterations for are when you're trying to find solutions to differential equations. When you're trying to find solutions to differential equations, also you could use this thing. Okay, so what we are going to do is basically what is it I'm looking at? Oh, let's go. So what we are going to do is basically try to see how you carry out this particular thing called an iteration. Now, for you to do an iteration, like I've said, you need a function g of x. Okay, you need a function g of x, so you need to come up with this function, a function g of x. Then this is the function we're going to use for our repetitive substitution. Apart from having this particular function g of x, you also need to have a value of x you're going to start with. So that's your starting value of x, which is your x naught, which is here. So you need a function g of x. You also need a value of x you're going to start with. And as you do this, as you put your x naught into this function g of x, we hope you're going to get other values of x from that particular process. So basically, this is basically what we hope to have. So you want to have a function g, and this particular function g, you're going to put in your value of x. This is supposed to be like this. You're going to put in a value of x. Then when you put in a value of x, this particular function is supposed to give you the next value of x, which is your x k plus 1. So you put in, if you put in x0 here, so if you start with k equals to 0, if you start with k, so you're doing an iteration, you start with k equals to 0, as you're going to see. So if your k is 0, then you're going to have your x0 here. Then this side here, you're going to have xk plus 1, 0 plus 1. So you're going to have your x1. So if you put in your x0 in this particular function should give you your x1. Like those things we're using for for the Newton-Raphson method. So if we start with, for example, x0. If we start with x0, then we start for k equals to 0. For if k is equals to 0, then this k here is going to be k equals 0. So you're going to have x0. So your formula is going to become g is equals to x0. Then here, if k equals to 0, you're going to have 0 plus 1. So you're going to end up with x1. So for k equals to 0, you've got g of x0. Then if you put your x0 in here, you expect to get a value of x, which is going to be x1. Is this clear on what we are trying to do?
Yes, sir, it's clear.
Then after you do this, so once you have found your value of x1, then you repeat this process. So the second time you do it, so we're going to call this k equals to 1. So for k equals to 1, this expression which you have here, so here where there's k, you put 1. So in this particular function, basically we are saying you're going to put this value x1, you're going to put it there. When you put x1 here, k equals to 1, 1 plus 1, you're going to end up with x2. So if you put your x1 value here, in this particular function g, you're supposed to get a new value of x, which is your x2. Then you do the same thing for the next, you do it again for k equals to 3. So for k equals to 3, if you put in for k equals to 3, you should end up having in your here in this g thing here, in this function of g, so you put in your x2, then you're going to get your x3, and this process continues like that. Now this process is going to continue. As you can see, there is probably no way of us trying to stop this process unless we set a criteria to say, okay, fine, we are producing values of x. Now we are going to stop when either these values of x we are producing are this close, or when we have done a certain number of iterations. Are we clear? Because we can't do this thing forever. So you have to set a condition, say, fine, I'm going to do this thing 50 times, or I'm going to do this repetition. Okay, 50 times doing it by hand is too much, but if you're doing it by hand, you can say, I'm going to do it 5 times, or I'm going to do it 10 times, and see if I'm getting closer to anything. Okay, but since we have got access to computers, you can also do this process whatever number of times you want. For example, you can do it 50 times, or you can do it 100 times, and see if you can get as close as possible to a certain fixed point, to a certain fixed value of x. Okay, now, like I've said, whether this function g leads us to a certain fixed value of x or not depends on how this particular function of g has been formed. There are certain functions of g you're going to create which will not lead you. So I think for starters, you have to do a trial and error kind of business. Okay, for starters, you have to do a trial and error business, because you're not really sure what kind of function will give me what you want. But after some time, we're going to set some criteria so that we see whether this particular function can work or this particular function cannot work before we waste our time in trying to do certain things. Okay, so basically, and the other thing is we need to have a way we're going to stop. So we can say ahead of time, okay, fine, we're going to try to do this thing for a certain maximum number of iterations, and also we can set a criteria where we say we can stop if the values of x we are producing, x1, x2, x3, x4, x5 become this close, then we can stop. Are we clear?
Yes, sir.
Yeah, so it's important to have that in mind when you're trying to do an iteration. It's important that you have in mind when you're going to stop. Okay, So a fixed point of a function g of x is a value of is a value where if you put this value in this particular function, what you're going to get is the same value. So what is referred to, what do we call a fixed point? We've been measuring fixed point. So basically what a fixed point is, it is a value or a real value where if we put it in this particular function, you put in, let's say you put in 2 in this particular function g of x. In g of x you put in 2. When you put in 2, what you get is 2 also. So when you reach such a point, when you find such a value is referred to as a fixed point. So if you, in a particular function g, if you put in the value p, then you get p out of this particular function. When you assign such a value, we call that a fixed point. Now, the method for trying to find this particular fixed point, that is what is referred to as a fixed point iteration. So you have to do this repeatedly. You start with, so you have this particular formula, xk plus 1 is equals to g of xk. For k equals to 0, 1, you keep on doing. It doesn't end anyway. It's up to you to see where this particular process ends. So we have got an example of a function which we can try to use for this particular purpose and see how this whole thing actually works and how it could actually end up. So the function we're going to look at in this particular case is g of x equals to e to the power minus x. Okay, g of x equals to e to the power minus x. So if we do this, if this is a function we're going to use, then our formula, our fixed point iteration formula, which is x is equals to k plus 1 is equals to g of x, g of xk, this is going to become, this formula is going to become, where there is g of x, we replace with this bit here. So our formula becomes the following: x is equals to, xk plus 1 is equals to e to the power minus xk. There's supposed to be a k here. Are we clear?
Yes, sir.
Yeah. So we end up having that. Okay. Now, we are going to start with this we're going to start with this value, x0, x0 is equals to 0.5. So, for x0 equals to 0.5, we're going to say, for k equals to 0, if k is equals to 0, then our fixed point iteration formula becomes, if there's, where there's k, you put 0, then you're going to end up having x1, so there's going to be k plus 1, 0 plus 1, so you're going to have x1 is equals to e to the power minus x0. Is that clear?
Yes, sir. It's clear.
Then we substitute our x0, we're starting with x0 equals 0.5. When you do that, so you're going to end up with e to the power minus x0 is going to give us 0.606530,659 as our value of x1. So from this value, we have found the value of x1, which is that. Then we repeat the process the second time. So we say, for k equals to 1, then our formula, our fixed point formula, iteration formula becomes x2 is equals to e to the power minus x1. Now we have got the value of x1, which is this one, which we have here. So we're going to put it there. So we're going to end up with e to the power minus 0.606,530,659. Then we're going to end up with x2, which is equals to 0.545239,211. So our x1, we started with 0.5, then we get x1, which is this. Now we've got x2, which is this. Then we proceed. We repeat again. For k equals to 2, our fixed point formula becomes x3 is equals to e to the power minus x2. We just got a value of x2, which is what we have here, 0.545239,211. So we put it here. So we end up with having e to the power minus 0.545,239. Oh, I've made a mistake somewhere. I think I've made a mistake. Yeah. So there's supposed to be 239. I've written 293.211. So I think this is what's probably causing one of the mistakes which I saw. Anyway, so you put in, I think I'll make this correction, but you put in your value of x2, which is what you have here. Then it's supposed to give you something which is what you have this, so you get your x3 like that. Then after you get your x3, you work out the process for k equals to 4, for k equals to 3. So for k equals to 3, you're going to get your x4 equals to e to the power minus x3. That's going to be e to the power minus 0.579 703 094. And when you do that, you're going to get your value of x4. So that's what you have there as your value, your x4 value. Then you repeat the process for k equals to 4. When you do it for k equals to 4, you're going to have your fixed point formula is going to become x5 is equals to e to the power minus x4. So you'll get your x4 value, you put it there, then you get your x5 value like this. So basically, this is how things work. Are we clear?
Yes, sir.
You repeat for k equals to 5. So your fixed point formula becomes x6 is equals to e to the power minus x5. So you have got x6 is equals to e to the power minus 0.571 172 194. Then you end up with this x6 is equals to 0.5 64 869247. Then you repeat again. So you keep on repeating this for k equals to 6. You end up with the fixed point formula x7 is equals to e to the power minus x6. So you put your x6 value there. So you end up having x7 is equals to e to the power minus 0.564 862947. When you do that, you end up with your x7 value being equals to 0.568 438 047. So you can see one of the things that you begin to see is there's a 0 and there's 5, then there's 6, 056 here with our x7 056, our x6 056, and this other number is changing. Our x5, it was just 05 7, so our 7 changed. Then this other previous iteration, the 6 has stopped changing. This other side we had a 0.54, so there was at the beginning there was a change, but the 5 was the same. Then the 5 started changing a bit, so here the 5 remains. This other one started changing, then it eventually became stuck at 056. Then here it's stuck at 056. Then after being stuck at 056, it goes to 057. It comes back to 056 here. So that is for 5. Then it's back at 056, 056, which is where we are there. Then for k equals 7, we work out the fixed point iteration formula. X6 becomes e to the power minus x7. So we end up with x8 is equals to e to the power this number. So you end up with x8 equals to 0566, then 409452. Then if you work out for k equals to 8, so you end up with, for k equals to 8, you end up with x9 is equals to e to the power minus x8. So you substitute that, they end up with 0.567, then whatever it is you get there. So you can see, as we keep on doing this process is, there are certain numbers it's at 0.56. Then there's some numbers which are changing. So basically, if you do this more and more and more, we expect to have we expect this whole thing to approach a certain value of x, which is not going to change very much. So if we do that again, so here, so we have k equals to 9. So your iteration formula is going to be x10 is equals to e to the power minus x9. So you do that, then you're going to end up with x10 is equals to 0.566 this 907212 like that. Then for k equals 10, so basically you end up with K10 equals to this much. So basically what you're trying to show here is the process you are going to go through if you have got a function of g of x, a function g of x, and you've got a starting value of x, which is your x naught. So this is the process you're going to go through, and as you go through this process, what we are hoping is that this whole thing is going to be approaching a certain value of x, where it's going a certain fixed value of x, such that if we get this value of x, okay, remember what the definition of a fixed point is. If we get this value of x which we have, we put it back in this particular function, we should be getting we should be getting the same value of x. Are we clear?
Yes, sir.
Remember what the definition of a fixed point is. It is a value, a real value, such that if you get this value, you put it in G. It's a value of P such that if you put it in G, it should give you back the same value. Okay. So the reason why you do this, when you find this fixed point turns out to be the solution to your function after you have a function which you have rearranged in this particular way. You have a function f of x. This f of x function is not your g of x. So you have got a different function, f of x. Maybe it's a quadratic. If it's a quadratic, we would say, let's say 2x squared plus maybe x plus 3. So if you've got a quadratic, for example, if you can write it somewhere, if you've got a quadratic function f of x, let's say equals to x squared plus 2x plus 3 equals to 0. Okay, if you've got a quadratic function x squared plus 2x plus 3 equals to 0, this quadratic function which you have as x squared plus 2x plus 3 equals to 0 is your function f of x. Are we clear?
Yes, sir.
However, from this f of quadratic function x squared plus 2x plus 3, I want you to write it somewhere, equals to 0, you can come up with a function of the form g of x. You can create a function g of x from this particular quadratic function. You can say, okay, fine, you will take the x squared and the 3 to the other side. So you end up with 2x is equals to minus x squared minus 3. Okay, then you divide both sides by 2. When you divide both sides by 2, you end up with x is equals to minus x squared minus 3 divided by 2. So what you have now is a function is x in terms of some function. What you would have done when you rearrange your expression like that, what you would have done is you'd have created this. You would have created this. You would have created this. When you have a function f of x is equals to x squared plus 2x plus 3 equals to 0, then you rearrange this so that the x is just on one side. Then you're going to have, on this other side, you're going to have a function of g of x. Are we clear?
Yes, sir.
Yeah, so you could have something like this. That's one way. So in that case, you would have x is equals to a function of g of x. And in this case, your g of x is going to be minus x squared minus 3 divided by 2 as your g of x. The other way you could do is you could get your x squared plus 2x plus 3 is equals to 0. Then what you do is you take the other terms. You leave the x squared on one side. You take the minus 2x minus 3 to the other side. Then you take the square root of the same on both sides. So you take the square root of minus 2x plus 3. So in that case also you end up with x is equals to g of x. And in this case, your g of x is going to be the square root of minus 2x minus 3. So there are different types. Basically, what I'm trying to say is when you're given a particular function, there are different types of g of x you can come up with. Some of the g of x you can come up with, they'll work quite well. As you do this iteration, they'll work quite well. They'll approach a certain value of x, a fixed point. In other cases, if your g of x is not so good, then in that particular case, your function is going to go away from any particular value of x. So, if in the case, like in this case, where you have got a good value of g of x, in this case we had e to the power minus x. If this is your g of x, then you start, then this whole thing approaches a certain value. It approaches a certain fixed value of x. If it wasn't for the mistake which we made in one of the steps which we did. Okay, so it should approach nicely a certain fixed point value of x. So there is a way to check if the function g of x which you have is going to work for this particular purpose or not. Are we clear? There is a way to check if your function g which you have selected is going to work for this particular process which you are trying to do. So the first thing when you create a g of x is this particular function g of x, your g, should be continuous in a particular interval ab. Okay, so your g should be continuous in a particular interval ab. So you select an interval, so you have this particular function you've created, then you select an interval ab, so it should be continuous in a particular interval. Then the other thing is there is also, you should be able to work out the derivative of this particular function. So you work out your g, you should also be able to work out the derivative. So both the function g you've created and the derivative of this particular function g, they should be continuous in an interval ab. Then of course there is a k. K is just a positive constant, but you're going to see where the k is being used. When you start, you select your starting value, your p, your starting value, or your x naught. When you select your x naught, which is the value you're going to start with, your x naught should be found in this particular interval. It should be in this particular interval ab. So you're going to select some interval in which you're going to use this function, and your function and the derivative of this function, they should be continuous in this particular interval. Then also your starting value, your x naught or your p naught, in this case the p naught should be found in this same interval. Then, as we have said, your function should be continuous in this interval ab. So the one thing you're going to do is you are going to try to work out the derivative of this particular function. Once you come up with the function g, how do you know that the function g is going to lead you towards an answer? So what you're going to do is you work out a derivative of this particular function. Then as you work out the derivative of this particular function, the absolute value for this particular function, the absolute value of this derivative should always be less than 1 for in this particular interval ab. Your absolute value, the absolute value of this particular function, the derivative of g of x, should always be less than 1. If you work out a derivative of this particular function g, then you choose a value between ab, your interval ab, or your starting value. You work out a derivative, then you put in your starting value. Let's say you put in your starting value, your x naught, in this particular function. Then the derivative of this particular value comes out whatever it comes out. Then the absolute value is greater than 1, is less than 1. Then that shows you that this particular function g which you have chosen is going to lead you to a fixed point, an attractive fixed point. Is what I'm saying clear? You have created the function g,
Yes,
you have created the function g, then you work out the derivative of this particular function g, and remember you've got a starting value, right? Your x naught. So you put your starting value in this derivative, This derivative is going to give you a value because you've put something there. Then you get the absolute value of the derivative. If the absolute value of the derivative is less than 1, then this function which for the function from which you have got your derivative, your g, is going to lead you to a solution. If, on the other hand, you come up with a function, then you work out the derivative of this particular function. Then as you work out the derivative of this particular function, you insert your starting value in this derivative. Then you get a value. Then the absolute value of this particular derivative, it can be positive or negative, but if the absolute value is greater than 1, then you know that the function you have will not lead you to a solution. So before you tire yourself into using a function, then only to find out that this particular function doesn't work, okay, you need to work out the derivative for that particular function. Then in this derivative for this particular function, you need to insert a value of x, or your x naught value, or your p value, whatever it is. Once this p value comes out of this derivative, if the absolute value of this particular derivative is less than 1, then the function which you have, your g function, is the correct one to use. If, on the other hand, your function comes out, the derivative of this particular function comes out to be greater than 1, the absolute value of the derivative comes out to be greater than 1, then this particular function is not the right one to use. Are we clear?
Yes, sir.
So what we did earlier is we assumed that our g of x, which is our e to the power minus x, is the correct one, and it works. But if you are going to solve problems using this particular method, you actually have to come up with a value of g of x, and a function of g of x. And with this particular function of g of x,
question.
yes.
What if is it possible to find the derivative, the absolute derivative, the absolute value of the derivative to be equal to 1?
If you find it to be equal to 1,
Yes.
it might be, but the
If it's so, what's the interpretation behind that?
I'm not sure what you could try and see if it actually, maybe it might work, or maybe might not work.
Okay.
Yeah. Okay. So basically, so when we meet at 12 hours, we are going to check certain functions. We're going to check their derivatives and see if these particular derivatives are going to give us some value which is less than 1 or greater than 1, and based on that we can decide whether we're going to this particular function which we have is the right one to use or not. Okay, so for now we have seen how you do an iteration, and we're going to end there for now. So we're going to meet at 12.
Thank you.
All right, just.